The process of landing on Mars was always an incredibly complex and challenging technical feat. Methods such as using giant airbags or sky crane systems, though creative, are not yet the optimal solutions for landing humans on the planet's surface. So, NASA has developed a groundbreaking landing system for the Red Planet, incorporating and processing data from SpaceX in a completely different approach from what was traditionally expected. Surprisingly, this solution may not be directly related to Starship. However, these studies will provide crucial info about the technical requirements that Starship will need to meet when it finally reaches Mars. Let's find out more on today's episode of Alpha Tech. Before delving into NASA's newly unveiled method for getting to Mars, it's essential to first grasp the challenges of touching down on this distant planet. Landing on Mars presents a set of challenges that are unlike those faced on Earth or the Moon, primarily due to its thin atmosphere. Mars's atmosphere is denser than the Moon's, but much thinner than Earth's, which creates a Goldilocks problem for landing. The thin atmosphere on Mars is too sparse to support Earth-like landing techniques that rely on atmospheric drag, such as parachutes or aerodynamic braking. The red planet's atmosphere is extremely thin, less than 1% as dense as Earth's. Terminal velocity on Mars reaches an astonishing speed of nearly 1,000 kilometers an hour, 4 times faster than Earth's. This means that atmospheric braking alone is insufficient to slow down a spacecraft. Leading space agencies around the world, including NASA, European Space Agency, and especially Russia, have faced this challenge repeatedly. During their efforts, they experienced multiple failures, even when attempting to land spacecraft on the Martian surface. Just recently have breakthroughs been achieved in addressing these challenges. A key issue that further complicates landing on Mars is the supersonic transition problem. Retropropulsion, where engines are fired backward to slow the spacecraft during descent, is a common method for landing on the Moon. However, NASA initially believed that retropropulsion could only work effectively at subsonic speeds below the speed of sound. The challenge with Mars is that during descent, the spacecraft is traveling at supersonic speeds when it first enters the atmosphere. NASA was concerned that firing engines at these high speeds could destabilize the spacecraft, as shock fronts would form around the vehicle, potentially causing significant turbulence or overheating. The shock from the engine plume could also damage the spacecraft, making retropropulsion seem impractical for Mars landings. Given these challenges, the idea of landing heavy payloads or even humans on Mars seems almost impossible. The combined difficulties of Mars's thin atmosphere and the supersonic transition problem mean the traditional approaches used for Earth and the Moon are simply ineffective, leaving engineers with few viable options. However, recent advancements in propulsion technology, particularly SpaceX's experiments with retropropulsion, have begun to challenge these long-standing assumptions, offering new hope for overcoming these obstacles. This breakthrough was recently revealed by Rob Manning, the engineer at NASA's Jet Propulsion Laboratory. Of course, for SpaceX, sharing technical knowledge is something they strongly support. This collaboration led NASA and SpaceX to jointly monitor SpaceX's Falcon 9 experiments through Propulsion Descent Technology Project from 2014 to 2017. To gather critical data, SpaceX's Falcon 9 boosters were outfitted with specialized instruments during re-entry burns. These tools captured key metrics like aerodynamic forces, thermal behavior, and dynamic pressures that closely resembled conditions on Mars. NASA used advanced techniques including aerodynamic modeling, flight reconstructions, and thermal imaging to analyze these burns in detail. By studying the interaction of retropropulsion within the atmosphere, the project provided unparalleled insights into supersonic descent dynamics. During its routine re-entry burns in Earth's atmosphere, Falcon 9 provided a unique opportunity to study supersonic retropropulsion, a critical technique for future Mars landings. These burns simulated the dynamics of entering Mars's thin atmosphere at high speeds, offering valuable insights without the need for dedicated Mars-specific tests. One of the biggest discoveries was the behavior of shock fronts created by the rocket engine's plume during supersonic reentry. Contrary to prior assumptions that these shock fronts would destabilize or damage a spacecraft, the data revealed that they form a protective bubble around the vehicle. This bubble reduces turbulence and heat, enabling a safer and more stable descent. The outcomes of this collaboration were transformative. The data collected not only validated the feasibility of supersonic retropropulsion, but also offered a clear path for adapting Falcon 9's re-entry techniques to Mars's unique environment. This foundational work has been instrumental in shaping NASA's strategies for developing human landing systems and advancing plans for crewed missions to the Red Planet. However, many unresolved issues remain when it comes to landing a crewed mission on Mars. Manning noted that there are still numerous unknowns, including how a large spacecraft like a Starship would be navigated and flown through Mars's atmosphere. The planet's thin atmosphere, while sufficient to create complications, isn't dense enough to significantly slow down a descending vehicle. Steering Starship through such an environment is complex, as its aerodynamic surfaces, like fins, may be ineffective at hypersonic speeds in Mars's tenuous air. This raises critical questions about how to maintain stability and control during descent. Additionally, the Martian atmosphere frequently hosts dust storms, which can reduce visibility, disrupt navigation, and increase thermal heating during entry. Wind shears, a sudden change in wind speed or direction, could destabilize a large vehicle like Starship, making controlled landings even more precarious. These atmospheric factors amplify the difficulty of landing safely and reliably. Once on the surface, Starship's massive engines pose another issue. During touchdown, the thrust could significantly kick up amounts of debris from the rocky Martian terrain, potentially damaging the engines. This debris could also jeopardize the vehicle's reusability for return missions. Designing effective protection systems for the engines is essential, as is engineering landing legs robust enough to stabilize a spacecraft of Starship size on Mars's uneven and unpredictable surfaces. Beyond the landing itself, infrastructure development on Mars presents logistical hurdles. Establishing durable landing pads to mitigate dust and debris is crucial but requires resources and planning. Similarly, creating systems to refuel starships for return journeys, whether through in-situation resource utilization or pre-supplied materials, is another challenge. The timing of Mars's launch windows further complicates progress. Due to the planet's orbit, mission opportunities arise only every 26 months. This limits the ability to iterate on designs and strategies quickly, meaning any failures could delay advancements by years. Overcoming these constraints requires careful planning, robust technology, and patience to ensure every attempt is as prepared as possible. Now, let's review some of NASA's Mars missions that have achieved significant milestones. From here, we can further reinforce the belief in SpaceX's achievable ambitions soon. The first successful landing on Mars happened in July of 1976 when NASA's Viking 1 lander touched down. The massive 1,270-pound lander dropped down from an orbiting mothership to make a three-point landing using a parachute and rocket engine. Viking 1's three biology experiments found no clear evidence of Mars microbes. The lander was powered by a plutonium decay-powered radioisotope thermoelectric generator and went silent in November of 1982, 6 years after completing its initial 90-day mission. Soon after Viking 1's success, NASA landed on Mars again in September of 1976 with Viking 2. In July of 1997, NASA celebrated the United States' Independence Day in its own unique way by landing the first Mars rover, the Mars Pathfinder lander, along with a small rover Sojourner on the Red Planet. Next, the success of the Mars Pathfinder and Sojourner rover led to a bolder and larger landing on Mars in January of 2004 when NASA's golf cart-sized Spirit rover bounced and came to rest inside the Vaskusev crater. NASA's twin rover to Spirit, the Opportunity rover, landed in January of 2004. Although it was expected to last only 90 days on Mars's surface, the rover actually survived for more than 5,100 days. The rover lost contact with NASA after a dust storm on Mars, and the mission was declared over in 2019. Phoenix lander touched down in May of 2008 using some equipment and tools salvaged from the lost Mars Polar Lander mission. NASA's flagship Curiosity rover completed an unprecedented sequence of complex landings in August of 2012, successfully performing a sky crane maneuver and parachute deployment to land on the surface of the Gale crater. NASA's InSight lander landed on Mars on November of 2018, allowing the first spacecraft devoted to probing Mars's interior to begin work. The mission measured numerous Marsquakes and helped gather data to better understand the formation of Mars and other rocky planets. The mission ended in December of 2022. The only failure of that mission was a mole or heat probe that was designed to move under the surface harder than expected. Regolith frustrated more than 2 years of efforts to dig more than a few inches. NASA abandoned the attempt in early 2021. NASA's ambitious Perseverance rover touched down on Mars on February 18, 2021. The car-sized rover is the most advanced robot ever sent to Mars. Perseverance, or Percy as it's commonly referred to, is busy looking for signs of ancient microbial life, to advance NASA's quest to explore the past habitability of Mars. Percy didn't travel to Mars alone. It was accompanied by Ingenuity, a Mars helicopter attached to the rover's underside during landing. Ingenuity went on to make an impressive 72 historic flights, becoming the first aircraft to achieve powered, controlled flight on another planet. Its final flight took place on January 18, 2024, when rotor blade damage brought its mission to an end. If the pinnacle technology triumph of the 20th century was landing humanity on the moon, then in the 21st century, the greatest technological feat would be successfully landing people on Mars. This is why NASA and SpaceX have joined forces to conquer Mars with Starship as early as the start of the next decade. NASA plans to send humans on a round-trip scientific mission to Mars, potentially as early as 2035. The journey will take approximately 6 to 7 months each way, covering a distance of up to 250 million miles per leg. Honestly, getting to Mars alone is already a monumental challenge, let alone establishing a settlement there. For this reason, NASA can't do this on its own. Collaboration with other space companies in the industry will undoubtedly be essential for such a mission. Among these, SpaceX stands out as the most suitable partner. The private company is currently leading in both rocket and satellite technology, critical components for a manned mission to Mars. Moreover, SpaceX's overarching goal, spearheaded by Elon, is to transform humanity into a multiplanetary species with a colonization of Mars as a key objective. As NASA's space exploration programs face budget uncertainties and increasing competition, the likelihood of the U.S. entering a race with China and other nations to establish human presence on Mars is growing. With Starship being the only spacecraft currently under serious development designed specifically for crewed missions to Mars, its rapid progress represents an advantage for NASA and its international partners. Starship will be the cornerstone of the entire Mars mission. Beyond serving as a transport vehicle, it'll function as temporary housing and provide support for resource extraction, facilitating the expansion of human presence on the red planet. The plan for Mars colonization follows a carefully structured, phased approach designed to maximize efficiency and safety while leveraging SpaceX's Starship as the backbone of the operation. Each phase builds upon the progress of the previous one, ensuring the gradual and sustainable development of settlements on Mars. Phase 1. Uncrewed missions. The first phase involves a series of uncrewed Starship launches to establish a foundation for human exploration. These missions will transport essential supplies, equipment, and experimental technologies to Mars, paving the way for future settlers. Critical tasks include testing automated construction systems, deploying power generation units, and mapping the planet's water ice deposits, a vital resource for life support and fuel production. Additionally, uncrewed missions will focus on validating entry, descent, and landing EDL systems to ensure safe touchdown on Mars. Advanced robotics will be deployed to set up initial infrastructure like landing pads and storage units, while also scouting for optimal settlement places. This preparatory phase is vital to reduce risks and provide the tools and knowledge needed for human survival on the red planet. Phase 2. Crewed missions. Once sufficient groundwork has been laid, the second phase begins with the arrival of the first human explorers. Crews of 10 to 20 people travel aboard starships outfitted as both transport and habitation modules. These starships will serve as the settlers' initial living quarters, giving life support, radiation protection, and storage for supplies. During this phase, the focus will be on acclimating to the Martian environment and expanding infrastructure. Crews will establish preliminary life support systems, including oxygen production from Martian resources and water extraction from ice. Initial farming experiments and small-scale manufacturing will also begin, allowing the settlers to test self-sufficiency techniques while relying on Earth-supplied resources. Phase 3. Advanced development. The final phase transitions from exploration to sustained development and growth. As the settlement expands, so too will its capabilities. The larger habitats, pressurized greenhouses, and solar or nuclear power plants will be constructed to support an increasing population. Modular design will enable scalable growth, ensuring that infrastructure can keep pace with the colony's needs. In this phase, in situ resource utilization becomes the cornerstone of Martian development. Technologies for extracting and processing local resources, such as producing fuel from carbon dioxide and water or building materials from regolith, will reduce the dependence on Earth resupply missions. And over time, this settlement aims to be fully self-sustaining, making its own food, energy, and essential goods. Ultimately, the long-term vision for this phase includes transforming the settlement into a thriving, self-sustaining Martian city. Of course, achieving habitability on Mars will also require efficient methods to utilize the planet's natural resources, particularly its water ice. Water is indispensable for supporting human life through hydration and hygiene, as well as cultivating crops with Martian greenhouses. Beyond life support, water plays a pivotal role in producing rocket fuel. By electrolyzing water into hydrogen and oxygen, settlers can manufacture propellants for return missions or even further exploration, reducing dependence on Earth. The discovery of significant subsurface ice deposits has underscored the importance of accessing and processing these resources at scale. However, extracting water from Mars's frozen terrain presents challenges given the extreme conditions and lack of liquid water. Technologies such as the red water system are proposed to address these obstacles. The red water approach combines coiled tubing which drills through ice-rich layers with rod-well techniques, a method adapted from Antarctic operations to melt and pump subsurface ice. This integrated system is designed for efficiency, allowing settlers to tap into buried reservoirs of ice. In addition to extraction, robotic systems and automated machinery will be deployed to enhance mining operations. These technologies can work continuously in harsh conditions, minimizing risks to human crews while maintaining a steady water supply. Then, as the colony grows, the need for large-scale water processing and distribution systems becomes increasingly urgent. Extracted ice will need to be purified for drinking and agricultural use and electrolyzed for fuel production. Centralized water processing plants will integrate these functions, ensuring a consistent and efficient supply chain. To distribute water across the settlement, a network of insulated pipelines and storage tanks will be developed, safeguarding against freezing temperatures and contamination. Modular designs will allow for expansion as the settlement increases in size and complexity. So, what about the natural environment on Mars? One of the primary challenges of landing on Mars is dealing with regolith, Mars's loose, dusty surface material. Without proper preparation, the immense force of rocket engines during landing could cause violent dust storms, debris hazards, and surface destabilization, endangering the spacecraft and nearby infrastructure. To address this, preliminary unmanned missions will deploy autonomous systems to prepare landing zones. These systems may include robotic graders to level the surface and spray coatings to bind regolith particles, reducing the risk of their disruption. Pre-laid landing pads constructed from local materials such as sintered regolith bricks could also play a key role in ensuring safe, repeatable landings. These pads would provide stable, debris-free zones, mitigating wear and tear on starships and minimizing environmental impact. While starships are versatile vehicles designed to serve as temporary habitats for early crews, they do present several risks when used for prolonged habitation. The thin Martian atmosphere offers little protection against radiation from the sun and cosmic rays, exposing settlers to some harmful doses. Shielding options include covering starships with Martian regolith or situating them in natural depressions to reduce radiation exposure. Additionally, environmental factors such as extreme fluctuations and the presence of perchlorates in Martian soil pose threats to health and equipment. Systems must be designed to maintain livable internal conditions and prevent contamination from the outside environment. Unmanned starships will play a critical role in mitigating landing and habitat challenges. These cargo missions will deliver essential equipment and supplies ahead of crewed arrivals, enabling the establishment of a safe and functional base. Automated systems can deploy inflatable or modular habitats, begin resource processing, and conduct thorough environmental assessments to identify potential risks. By addressing these challenges in a phased manner, the mission architecture ensures that the first settlers will arrive in a well-prepared environment with minimized risks and an increased likelihood of success. A critical component of this plan is the regular deployment of Starship missions to Mars. SpaceX proposes doubling the number of launches in each 28-month Mars transfer window, eventually reaching a cadence sufficient to support large-scale infrastructure development and population growth. While the reusability and cost efficiency of Starship make this goal theoretically achievable, it demands an unprecedented level of operational reliability, launch pad readiness, and production scalability. Any delays or failures in the launch schedule could trigger a ripple effect on mission timelines and resource availability. Sustaining human life and building self-sufficient settlements on Mars will require a robust infrastructure. Water systems must not only support life support and agriculture, but also produce fuel for return missions. Similarly, power grids capable of meeting the energy demands of habitats, in situ resource utilization processes, and industrial activities must be deployed and maintained. Extracting and processing local resources such as regolith for construction materials or ice for life support will require advanced automation systems and equipment capable of withstanding Mars's harsh environment. Developing and deploying these systems will be both time intensive and resource heavy. The colonization of Mars entails numerous risks stemming from the planet's remoteness, extreme conditions, and the complexity of the missions. Communication delays of up to 22 minutes round trip mean that crews and systems must operate autonomously, increasing the risk of errors. The harsh environment, characterized by intense radiation, low temperatures, and dust storms, poses significant challenges to both human safety and equipment reliability. Moreover, the margin for error is incredibly slim. Launch failures issued with in situ resource extraction or habitat breaches could jeopardize not only the mission's success, but the lives of those involved. The vast distance between Mars and Earth complicates resupply and rescue missions, making pre-mission planning and risk mitigation strategies essential. While the proposed Mars plans represents an inspiring leap towards humanity's multiplanetary future, achieving its goals requires balancing ambition with realism. Incremental progress, rigorous testing, and collaboration between public and private entities will be key to mitigating risks and ensuring that humanity's first steps on Mars are both bold and sustainable. That's all for today's episode. Thank you so much for watching, and see you next time.